Hi, everybody. Let's talk about quantum physics. And in this case, it's going to be about a particle in a one-dimensional box. What difference between quantum physics and classical physics? Classical physics is mean a particle is particle. It has momentum and it has kinetic energy. But for quantum physics, it's just like duality. A particle can behave like wave and particle. And the most different is that for the energy level, quantum physics particle can have a certain energy level or discrete. It have a certain energy level that a particle can occupy. But for classical physics, a particle have has the continuous energy level. That means it can have any energy level. So that's the big difference. Okay, what is the particle in the box? We will go through that you have a box which with the width L. Okay, just like this the figure. The particle is confined in the box. That means cannot escape from the box because there are two walls, right? Left and right. And at the wall, you have infinite potential, both of them. But in the box, the potential is zero. But it doesn't mean electron have zero energy. It has energy that we will define for the energy level of the particle. And the particle is there move along the horizontal line. Okay. So what we're going to do, we will define the wave function. I will put the wave function as psi. Okay. And the psi symbol is just like this. We will find the wave function at any particular x, position x. This is your psi. Okay. Just make don't make you confused about the sinusoidal or cosine. You know, we will define the wave function when we have the wave function at any particular position x. You'll be able to find the probability to find the particle in the box, and you can do that by do psi square. And the last one, we will define the allowed energy level of the particle that's confined in the box. That's why they introduce very simple equation, Schrodinger equation. That's the second derivative of wave function. Okay, here. This equation is simply concerning about energy. You can see that the first term here is the kinetic energy, and the second term is the potential energy, because you need to consider that total energy that's the in general is equal to the kinetic energy add up with the potential energy, right? That's very simple equation, but the Schrodinger equation is look like very complicated, but it's not. You have m, you have h bar. M is their particle mass. H bar actually equal to h over 2 pi, where h is their Planck constant, you know that. So your job is to solve the Schrodinger equation, to define the wave function, to define the probability, to define the energy level. That's all. Now it's more simple because the Schrodinger equation, you have a total energy rate equal to kinetic energy plus the potential energy. But you just consider only the particle in the box, not outside the box. Outside the box, you have no wave function because the particle cannot escape from the box. Inside the box, the potential becomes zero, so the potential term in the Schrodinger equation is drop out. So it's easier, for you to solve the problem. And this is the second derivative equation. You differentiate the wave function with respect to x. That's their first year calculus. Finally, you have the wave function of x at any particular position x equal to a psi kx, where a and k are constants. Very simple equation. That's your wave function. And you can work out. You can get a equal to square root 2 over L. Just depend on the width of your box. And k is also constant. It depend on the n, when n is the integer number. Again, psi x equal to a psi kx. To work out how to find a and k, you simply apply boundary conditions. What is boundary conditions you have here? Well, you have the box, right? So you have psi x equal to a sinusoidal, and then kx. The first boundary condition, because you have two variables, right? A and k. So you need two equations. The first one is that you apply psi of x equal to 0 because it's as the wall on the leftmost. So you have no wave function. The particle cannot escape, from the box. So it has no wave function. So your wave function psi of x equal to 0 is 0. And the second boundary condition is that at the rightmost x equal to L. So psi of L also becomes 0. You have no wave function. Finally, you can work this out. You end up with a equal to square root 2 over L. And your k also depend on the mass of the particle, the width of the box. That's it. And you work out further. You have k depend on n, because where is n from? Well, for your psi equal to 0 and psi equal to a psi kx, psi of 0 is, of course, is 0. But for the other boundary condition at x equal to L, your psi or the wave function going to equal to psi or KL, but it has to be 0, right? Then psi have to be 0. So your KL has to be what? In pi, right? Because you know psi in pi always equal to 0. And n is your integer number. And sorry, you can work out more and you will end up with the energy level En going to be equal to this term. Okay, also depend on n. The rest is just only a fixed number. You have the Planck constant, that's the fixed number, and you have the mass of particle, and you have L. Okay, they are divided. So sorry, when you already defined your wave function psi of x, you can find the probability for the particle is located. Simply do the psi square. And if you do the integration from 0 to L over psi square x, or the wave function square dx, that's mean only in the box. Of course, you definitely find the particle, so you get the result become 1. You can try by yourself. Now, if you take a look at the plot, since we already defined the wave function, and okay, just right here. That's your wave function for n equal to 1. This is n equal to 2. And this is we call node, whereas the particle has the 0 energy. And for the probability, you can do the wave function square. So this one, the shape doesn't change, but this one, you have a negative wave function, right? So negative become positive. So just look like this. The higher number of n, the more nodes, no doubt about that. Now, the very important thing is that the energy level, as I mentioned earlier, for a quantum effect or quantum physics, the particle can occupy only a certain energy level, or the energy level is discrete. That's the different than the classical physics, whereas the particle can have any energy levels. So that's the continuous. That's the different. That's the big difference. Now from the energy level En, that's the depend on n square. You can do n equal to 1 and n equal to 2, and you get a higher n. This is your plot of our energy level. Is there, for instance, is there a lower number, you have a larger space between energy level. But when increasing, for example, n equal to 10, n equal to 12, the energy level tend to be getting closer. And finally, when n is a very big number, the energy level will overlap. So it just like strip. It's like continue as the energy level. So that's why for higher n, or in quantum physics, a particle can behave like a wave or particle. That's duality, right? And for higher n, classical physics is applied. For the lower n, the quantum physics is applied. Okay, hopefully this will make you clear understanding about what's going on. So that's why let's make a conclusion. You want to define the wave function. Okay, you start from you're working on a particle in a box, one dimensional. You want to define wave function because in quantum physics, a particle behave like a wave. So you're looking for the wave function, and you do the wave function square. Let's give you the probability for the particle is located in the box at particular position of x, and then you define the energy level En. To do that, you apply Schrodinger equation, and you solve the Schrodinger equations, which is the earlier the energy equation. The total energy equal to the kinetic energy add up with potential energy. And then you analyze the wave function, you analyze the wave function square, that's the probability to find the particle in the box, and you analyze the energy level. That's all. Okay, thank you very much.